So we have arrived at the last talk for this session. It's given by Ilya Agapov. Ilya received his undergraduate degree in applied mathematics from Moscow State University in 2001 and PhD in accelerator physics in 2005 from DESY. And since then, has worked on beam physics and radiation theory, simulation, and acceleration design and operation at Royal Holloway University, London, at CERN and also DESY. He will present online optimization of XFELs and light sources with OCELOT.
Thank you for introduction. So I'm actually, contrary to the announced abstract, I'll focus on the XFEL, which has been commissioned in operation at DESY. So the authors are listed here. So first I'll start with the introduction to OCELOT. So this is the project which is started as a purely simulation project for undulator and FEL radiation for European XFEL. But then we were faced with the problem of benchmarking simulations with reality, and it turns out that FELs are very difficult for this kind of cross-checking. Because of diagnostics is not trivial, so the bunches are short and small, and the synchronization is not trivial. Moreover, there's always need for manual retuning. So, driven by the need to compare actual simulations with results, we kind of branched into more controls-oriented developments. And the kind of resulting concept is a simulation framework and library which features various components like the electron beam physics, X-ray physics, and online data control. And moreover, this framework is also features advanced GUIs, meaning some kind of GUIs suitable for real operation of the machine. And we try to make it data-centric, so we try to make use of various, I'll say, data science approaches. So some kind of simulations results from OCELOT are shown in this slide. More technically, everything is in Python, so we focus on simplicity because we have limited resources, so we have to cover a lot of ground. So we don't provide any API to any other languages other than Python. So everything is a Python object. We completely skip, let's say, the I/O or serialization or any input language, which is everything is just Python. So it makes things, of course, much easier. And this kind of code actually makes up 90% of any beam physics code, and we throw it away for simplicity. Of course, Python is an ideal language to provide parsers to external codes, external inputs, which we also provide, but it's actually not a baseline. So Python has, as everyone knows, abundant numerical libraries for both numerical simulations, plotting data, for parallel processing, and for machine learning. OCELOT is not a standalone application, but a Python library plus a set of tools. The code is optimized when possible, but we kind of prefer simplicity and always and usability to performance. So we used to have some OpenCL code, which we discontinued for this reason. This has model of physics and architecture, which is inspired by systems like Gen 4 OpenFOAM, so that it's designed so that physicists could actually introduce their additional modules. And it's open source and freely available. So more technical details, some physics which is included is single particle electron optics, beam dynamics for Linux, including collective effects like wake field, CSR, space charge. We have some X-ray optics models, and we have synchronous radiation solvers for undulator and bending magnet radiation. The only thing which is actually externally introduced is the FEL calculations with Genesis. And I'll focus on the controls and in the controls interface and optimization tools within the OCELOT framework in this talk. So there's a GitHub site where I can look at the code and download it. And there's a NIM paper which describes the concept in more details. We have a Jupyter notebook for tutorials, which we also misuse as a test suite. So one can have a basic look at the code in this Jupyter notebook on the GitHub So now coming to the European XFEL. In a nutshell, so there have been 2 talks at least on the controls for European XFEL accelerator and European XFEL beamline controls. It's a 17.5 superconductor LINAC at Hamburg, which drives 3 undulated beamlines, one of which has been now commissioned in operation. It's the most complex FEL currently in operation. Now the optimization and tuning of such a machine is non-trivial. So even when all the major technical subsystems work well, getting photon pulse parameters which are close to design is non-trivial. So one has to resort to extensive manual or fine-tuning. And the subsystems which are used for this tuning include the GAN, the RF, voltages and phases, parameters, orbits, optics, undulator gaps, phase shifters, and other systems on the high level only, not on the low level. So we have hundreds of free tuning parameters, and this actually requires times expertise. Setting up the machine requires times expertise, and the result is different depending on who is doing this and how much time is invested in such tuning. And we recognized this early on and made some tests on a flash to prepare some software for a European XFEL which would address this. In this picture you see a kind of a statistics plot for a flash for the soft X-ray free electron laser DESY, which has been in operation for like a decade now at Hamburg. And this shows statistics of the SASE, of the photon pulse energy as a function of wavelengths. And one sees that what the performance one is able to achieve varies greatly depending on the tuning. So these dots in this plot show individual tunings for flash, and on the right you see something which says to machine learning. It's a k-means prediction of the photon pulse energy of flash built on the basis of statistical data. But the message of this is that the performance of the machine, there's kind of sweet spot, and the performance of the machine is not uniform. So it depends actually on who is doing this and how much time is dedicated to this. So these are the results of initial results from flash, right? So we introduced like an empirical. So the idea is apparently not new. One can just, instead of trying to optimize things in simulation, one can take the real data from the machine and optimize it with a numerical method, like a simplex. And we used, for flash, we used parameters like undulator orbits, optics matching, and compression to empirically tune the FEL, and we implement it as a tool. And this is some results for flash are shown in this picture. So typically, you could tune the photon pulse energy much quicker than an operator would do. Not necessarily better, but at least quicker and with less trouble. And this is described in some publications before. Now coming back to the European XFEL. So actually, the initial idea of the optimizer that one would run through a sequence of actions, or basically a decision tree of actions, and going back and forth between groups of parameters, actuators, and try to tune the photon pulse energy or other relevant parameters with that. But that appeared to be very difficult for in operation, because when the program is running for a long time, the operator is not aware of what is going on, when it's going to stop, and things like this. So we changed this to a more simple system, which actually uses just one set of parameters, but features a more advanced GUI, which is more usable by an operator. So this GUI shown here, it's possible to load a set of actuators from a config file, and it has a certain device limits and certain plots for the objective function and for the actuators. So this was changed to be completely generic, meaning that one could they are predefined objective functions like the SASA energy, but one could also by dragging and dropping devices from the control system, one can define custom objective functions with a Python expression which is available through this GUI, as well as through a completely custom script, Python script, which one can add to the system. There's also an alarm panel, so one could define an alarm, meaning that a certain detector is not reaching certain. is not within certain limits, so the optimization will be paused until the problem is solved. So apart from the SAS optimization or the photon pulse energy optimization, the system can be used for a variety of cases. So first is the dispersion correction, so it's things like linear optic correction for LINAC dispersion orbits or optics are typically done with a response matrix-based method, meaning that there's a model, linear model, which connects the correctors to BPMs, and then by inverting this system, one can always correct the orbit to 0. And this doesn't always work when the model is not known, which can happen actually for LINACs. Especially in the initial stage of operation. So in some cases we were correcting dispersion with, the dispersion was corrected with a purely empirical simplex method shown in this picture. This optimizer was also used for beam loss and orbits correction, so that transmission of the beam through the LINAC is a typical task which has to be done for a setup of the machine. And when a large part of the beam is lost in a LINAC, it's not good, especially for a superconducting machine. And such losses were sometimes optimized with this generic tool. This is the standard use case for this optimization. This is SASE pulse energy optimization. The two examples are shown in these slides. So for us, one on the right is with the quarter pulse in the so-called dog-leg section of the European XFEL LINAC. And on the left is the typical optimization with the so-called launch tiers on the later section. So the comment is that to make this generic, we always solve the minimization problem. That's why all the plots show a signal going down instead of up, which is sometimes counterintuitive, and we have to deal with that actually in the next version. So apart from these completely model-independent tuning tools, of course, OCELOT has the beam optics model, and there's an input deck for European XFEL is in place, so we can also build tools using model-based correction approaches. One of the tools, which is a very standard orbit correction tool, which is shown in this slide. It's a completely standard tool, but just to mention that it's also in place in OCELOT. Something which has been extremely useful for us is based on this idea from Letra. So the optimizer based on simplex or any other method actually cannot be effectively used during beam delivery to the users, because the objective function, which is, for example, the photon pulse energy, which changes noticeably during the optimization process, which is not compatible with beam delivery. So we implemented a method which was proposed here from Letra, and which we call adaptive feedback. So what it does, we correlate the photon pulse energy with the orbits, and take the statistics for the past 500 shots, and take the 10 best percent in terms of photon pulse energy, compute the orbit for this 10 best percent of photon pulses, and correct the orbits to this value with an SVD-based approach. And this works actually great for user operation, and typically is during initial stages of user operation, this feedback was always used. Something else which we introduced is called online model. So since OCELOT has this beam physics model, we can just simply make a GUI on top of that using PyQt, which is a standard tool. And this shows this kind of online model for European XFEL. You can then tweak various parameters like the quarter poles, phases, and so on, and see what the changes in the optics are supposed to be. So this kind of tool is actually in use for hardware machines like LHC, but we're not sure how to use it for our machine yet. But this possibility of using such kind of tool is being explored. Another tool which is part of OCELOT suite is the correlation tool, and this is the part of our, which is kind of is in the spirit of data-centric software, and this just plots online real-time correlations of various parameters. And if you choose the parameters properly, like in this case, the correlation of the orbit with energy, you can have useful information like the online dispersion in this case. So I'm finishing here. So this is the last slide. So machine learning is apparently is a big deal here in this community, and actually it has been used a lot in astronomy and particle physics, but we still have to exploit the data from our LINAC, which is shown here, which is a very complex system, and cleaning this data and effectively storing this actually is a challenge which you have to address before effectively using any machine learning approaches. So I'm concluding that the empirical optimization has been successfully used for repeating XFEL, commissioning and initial operation. The corresponding tools are open source and available with OCELOT, and the challenges we have to address are exploiting beam physics models to restrict our search space and exploiting the statistics and machine learning for implementation. Thank you for your attention.
I just want you to comment on how easy do you see for this to be used in a different facility. So the type of physics that you are currently supporting, and also whether this has any other hidden dependencies on your own IT infrastructure, for example.
No, this is. So actually, this is there's a very clear layer of controls interface, and the same is used at LCLS, and they introduced their own optimizer, which is called Gaussian Process Optimizer, in the OCELOT. So it's very easily adaptable. There's another facility where there's a small synchrotron called Siberia 2 that has been used for a synchrotron on FEL, and we tried this for Petra, but there's nothing definite there. But it's easily adaptable to various PyDux and PyEPICs easily interface to this.
Thank you.
Other questions?
Yeah. Thank you very much for your presentation. I have a question regarding the OCELOT orbit framework. Is the orbit correction done completely on the software, or is the hardware platform?
No, it's just a standard thing. You compute your response matrix with the beam physics model, and then compute the inverse. Take the reading of your orbit, invert it, and it's software.
And this is done completely using the framework.
Yeah, it's just simple. It's very simple to do with this framework, because it's just if you take away the graphics interface, it's few lines of code actually. So for the code is GUI, with 4 lines with OCELOT.
Okay, thank you.
The bottom.
Right.
It's okay. Our, let's say, experiment of Sakura, and that time beam energy, maximum beam energy, and beam shape is very round shape, but user want a round shape beam and the maximum peak energy,
right.
But both are not satisfied in same time, many things. So how to compromise that kind of situations?
Right. So you mean the bunch lengths, right?
No. Shape.
Shape. What is shape? Bunch shape, like the
transverse profile.
Transverse profile.
Yeah.
Well, profile. I mean, this is supposed to be Gaussian, right? Always. The profile, I mean, we have I'm not sure about the profile, but the pointing, sometimes, I'm not sure about XFEL, but at Flash we see the profile which is not Gaussian. This is true. But I mean, my understanding that typically is because there's no FEL saturation, yeah? If you optimize the power, you would also go beyond saturation. That should be also Gaussian. It's my understanding, maybe I'm wrong. But also the problem is also the pointing, yeah? So if you have to keep the pointing also. We deal with this also. But we found out that if you do this simultaneously in one objective, it doesn't work well. So you have to just do it iteratively. You iteratively optimize the pointing, then now the pulse energy, again the pointing, and if does it answer your question? Or
because of the beam itself, real life is not perfect Gaussian.
Sure.
So sometimes it's asymmetry, it's in the band shape, and SASE select some kind of peaking somewhere. So that's not a good shape for users.
Sure. So we haven't done this, just to answer your question. But thank you for your comment.
Yeah, very last question, if it is very short.
Actually, it's very, brief question, yes or no. Do you have any plans to do beam-based alignment in the undulator section by using an OCELOT?
I don't have these plans.
No, you don't.
I don't have these plans. But someone else is doing beam-based alignment using
OCELOT.
You have to talk to, no, you have to, no.
No? Okay.
You have to talk to Yuhui Lee, right?
Yeah, this I know, but I mean you don't have any plans to implement this feature in the OCELOT? No?
No, we can do everything, right? So.
Okay.
Okay.
Thank you.
Thank you, speakers. Again.